Okay, let's do this. So we're working on project 3. We're past task 1 and task 2, and we're trying to get you through task 3 in the application objective. So we learned about graphs last time, and I kind of just mentioned what breadth first search is. Breadth first search is what we're going to use for task 3 and the application objective. So our ultimate goal here is to get our AI pathfinding working properly so it doesn't get stuck on walls. We're going to do that in a few parts. Task 3, this distance avoid walls method, is going to find the distance between any two grid locations, or rather the distance between the two input grid locations, while avoiding walls. So this would be the number of grid locations an AI would have to traverse in order to move from, or human player, to traverse from the start grid location to the end grid location. So we want to compute the distance, but avoiding walls. So if there's a wall right in between the start and end, the distance should calculate by going around that wall. And then AI, this closest player avoid walls, which is going through all the players in the game and computing the distance from the reference player to all those players by calling your task 3 code to find the closest player in terms of that task 3 distance. And then finally, the one we're really building up to is get path, which will get the path to the closest player from that AI's current location while avoiding walls. So this is the actual path that we want our AI to take when it's traversing through the game. You return that path, and then the rest of the game code that was provided for you is going to take that path, figure out which vector that AI should take to be able to traverse that path. So that's what we want to do. And we're going to get all the way there today. We're going to get there today, and then Friday is going to be examples, mostly test cases, how to test, at the very least, task 3, and maybe a little bit talking about the application objective. So let's do this. Let's figure out how to do all that stuff. Do the lecture slides work for y'all? Try refreshing the page. If that doesn't work, let me know. They should work, though. That's why I always download the slides. You can see me always going from the course website. That's just to make sure that if I did make a mistake and the slides aren't working, I would notice it during lecture and I could fix it. So they should be working. But I did change the file name of today's slides, so you might have to refresh to get the new file name in the link. Thank you. Good. Sounds like that worked. Pathfinding with BFS. Let's do it. So we got a few definitions to talk about first. We mentioned path briefly last time, so this one is more of a reminder. But path is going to be a sequence of nodes where any two adjacent nodes in the path are connected by an edge. So a path in this graph, this would be a valid path, Lincoln to MIT, to Utah, SDC, RAND, UCSB, SRI. This is a valid path in the graph. And the new definition, the length of a path, which I think I mentioned last time, but I didn't have it in the slide. It wasn't formally part of Monday's content. The length of a path is going to be the number of edges in that path or the number of nodes minus 1. Both things are going to get you the same information. So the length of a path, if you're thinking of this as grid locations, if I'm at this grid location and I can move 2 grid locations to get to my destination, that would be a path of length 2. It's the number of hops I had to take to get from start to end would be that definition. So the number of edges or number of nodes minus 1. The length of a path, and then distance is the length of the shortest, or at least a shortest path between 2 nodes. So, for example, Lincoln and SRI, the shortest path between them is going to be 3. 1, 2, 3. We can stare at this graph all day. You're never going to find a path between Lincoln and SRI that's shorter than length 3. You're never going to find a path of length 2, or of course 1. So that's the distance between those 2 nodes. The distance between 2 nodes, the length of the shortest path. So for task 3, distance between those 2 grid locations, the length of a shortest path between those 2. RAND and BBN, they're connected by an edge. That's as That's a shorter path you can get, just one hop and you're there. Distance 1 if they're connected by an edge. There is, well, a little bit short. I shouldn't have worded it that way. Like BBN to itself, that would be a path of length 0. You're already there. The start and end are the same node, path of length 0 to get from that node to itself. The path would just be the node BBN, and that's it. Path of length 0. Carnegie to SRI, as we're going to see when we run breadth first search, I'll claim right now that it's distance 5. You can stare at this graph for days. You're never going to find a path between those two nodes of length 4 or shorter. Not going to happen. They're distance 5 from each other. So this is what we want to compute in task 3, is distance. That's what we mean by distance, the length of the shortest path. The length of a path is the number of edges in that path, or the number of nodes minus 1. What we want to do is find distance between nodes using breadth first search. I briefly said what breadth first search was last time. I didn't go into any detail about it. Today we're going to go into tons of detail about it to figure out how to actually use breadth first search to get useful information. There actually is a lot of useful information we can get out of the breadth first search algorithm by adding a little bit of structure and bookkeeping on top of it. And eventually we'll find the shortest paths for the application objective. So let's run through breadth first search again. Last time I kind of just waved my hand and say explore the neighbors of the neighbors, and just keep doing that until you're done. But how the hell are you going to code that? You can't, obviously you can, but there's a lot of design work to do there. So I want to take some of the guesswork out of the design of that algorithm out of your way for you to make task 3 a bit more manageable. And instead of just keeping track of the nodes that have been explored and then exploring neighbors of neighbors, I'm going to keep track of a little bit extra information here. I'm going to keep track of the edges that we used to discover new nodes. And we're going to start at Carnegie this time. Last time I started at UCLA for all the examples. Today we're going to start at Carnegie for all the examples, just to switch things up a little bit. So I'm going to keep track of how we found each node. And I'm going to start with the starting node. And I'm going to be very careful about how I draw this in the slide. How I draw this thing on the right, this new graph that we're going to create that only contains the edges that we used to explore new nodes. I'm going to draw my starting node at the top. And every time I explore a new node, I'm going to add those nodes and the edges that discovered them, and I'm always going to draw the new nodes down on this graph. My start node at the top, and then each time I discover a new node, we're going down visually. Case and Harvard are going to explore Lincoln and BBN, so I'm going to draw those edges down. And then either Lincoln or BBN could explore MIT. We have a tie here. That we are allowed to break arbitrarily. It doesn't matter which one of these edges we take, as long as we take one of them and not the other. So I'm going to say Lincoln ended up finding MIT and BBN only discovered Rand. I'm going to draw those down. And this edge that wasn't used to explore any nodes, I'm not going to draw in my graph to the right. So this node between MIT and BBN, I'm just not going to draw it in my graph on the right. I'm going to keep doing this. MIT is going to discover Utah. Rand is going to discover 3 separate nodes. Again, all edges going down. Utah is going to discover SRI. SRI could have been explored from any one of 3 nodes. I just chose Utah arbitrarily. And then UCLA is going to discover Stanford. And now by doing that, we have a new graph, but with any of the unused edges removed. And what we end up with is a tree. We have what we call a breadth first search tree, which is going to show us all of the paths that we used to discover each node. So it is a tree because it has no cycles. Any graph with no cycles is technically, by definition, a tree. It's got levels. So the way I very carefully drew this visually, so everything went down, and each edge that I added had the same height. So I kept this, nice and organized here, so I could draw this slide. But this does have levels. If we label each one of these visually as a level, what we get, the information that we can extract from a run of breadth first search, is that for each level in the graph, any node at that level has a distance to the starting node equal to that level number. So these nodes at level 3, MIT and Rand, they're on level 3, therefore they have distance 3 from Carnegie, and in fact these paths are shortest paths from Carnegie and MIT. For MIT specifically, we know there are multiple paths, but the other one that we chose, that we broke the tie arbitrarily, was also length 3. There's no path shorter than length 3. We have this 1, 2, 3, the path we found. The tie we broke arbitrarily, 1, 2, 3, it still would have been on level 3. So for our purposes, for distance and pathfinding, we don't care about breaking those ties as long as we have the right level and the right distance for each node. And we can see I claimed SRI was distance 5. Breadth first search is confirming that. It's on level 5. It's got to be distance 5. This is just a fact of breadth first search. You run the algorithm. This is the information that you get. You'll prove why when you get to 331. I don't think you do that in 250. But in 331, you'll prove why this is the case and do some fun stuff with the math. For 116, I'm just going to say this is a fact of breadth first search, and we'll take it as fact and move on. But SRI, between SRI and Carnegie, in this graph, you're never going to find a path less than 5. And I can say that confidently because breadth first search confirmed it. When we found SRI, it has distance 5. It was on level 5. Where I found a path of length 5. There can't exist a path of length 4, or else breadth first search would have found that path. The fact that it didn't find any path of length 4 and it put it on level 5, distance 5. There's one big problem with this, though. Kind of the same problem I alluded to earlier. How the hell do you code this? When I did this on the slide, I'm just going to visually draw things down and then draw these dashed lines and call them levels, and that's my distance. How the hell do you put that in code? You're not going to write some code that says, okay, computer, visually make that lower than the other one, and then draw these lines. You're just not going to do that. So I want to take this concept, but put it in a way that we can write in our code. So this is where I want to show pretty much how to do task 3, to be honest. This is the idea of breadth first search, and then connecting it to the homework code using grid locations and AI players and stuff. That'll be the jump from the slides to the homework. But let's see how you're going to run, once you're ready for breadth first search, how you're going to use breadth first search to compute these distances for task 3. So for this, we want to use some data structures. This is the pinnacle of the data structures and algorithms learning objective of the course. So let's use a whole bunch of data structures, right? And of course, this is designed to get you using a bunch of data structures. So we're going to take some data structures and use them to write your code. So this is the idea behind breadth first search. We're going to use 3 separate data structures for your code. You're going to use one to keep track of which nodes you're about to explore the neighbors of. One data structure to keep track of which nodes have already been explored. And a third data structure to keep track of the distance from the start node to any node in the graph. 3 data structures. So for the first one, the order in which the nodes will be visited, we're thinking Q for that. For this one, I recommend using Scala's built-in queue, import queue, and then just use that queue in queue and dequeue. Much opposed to a stack. If it were a stack, I would say use a list. With a queue, since you have to work on both ends of it, it's just easier to import queue instead of using a linked list and trying to work from both ends of a linked list. Besides the fact that that's inefficient, that's not too much of our concern in 116. It will be in 250, but it's a little bit tougher to work with. If you want to use a list for a queue, I'm not stopping you, but it's a little bit easier to just import queue and then use that idea in queue and dequeue as your two method calls. So a queue to keep track of the nodes that should be visited. That queue is going to make sure that you visit nodes in the right order. We want to make sure we visit nodes in the right order, or else everything falls apart. If you use a stack instead of a queue here, you're done. Like it's not going to give you what you want. Fun fact: if you use a stack instead of a queue, you end up with depth first search instead of breadth first search. That's the only difference between the algorithms: is a stack versus a queue. We want breadth first search because it gives us this distance and pathfinding information that we're going to need for our AI stuff. Depth first search just doesn't give us good information that we can use in our game. So we don't want a stack; we want a queue. We want another data structure. I like to use a set, but I had never showed you sets in Scala. You know about sets, those of you taking 191. It doesn't allow duplicates and easy to check if a set contains a specific value. So that is the data structure really called for here. But I assume a lot of you will just use a list because that's the data structure we've been using, and it'll do what you want. So one data structure, I'll just refer to as a list from here on out. But a list which is going to keep track of which nodes you've already visited. Visually, I'll mark them as orange on the slide. So a node in orange would mean that node is in your list that's keeping track of which nodes have already been visited. And finally, the new one, conceptually at least, a map to keep track of the distance from the start node to any other node. Now, I'm populating this with just initial values. I put infinity for all the nodes that haven't been explored yet because we don't know their distances. We haven't found a path from the start node to any other node yet because we haven't started running breadth first search yet. So I'll initialize them to just whatever. I put infinity symbols here. In my code, I usually use -1, and then I have checks. If it's -1, it means I haven't discovered that node yet. I don't know its distance yet. But I do know the distance of one node, the start node. From the start node to the start node, distance 0. We're already there. Don't have to move at all. We're already there. It's distance 0. So we have a queue to keep track of the order in which we're going to check nodes. And by check, I mean check all the neighbors and explore them if needed. A data structure, a list probably, to keep track of which nodes have already been explored, and a map to keep track of the distance from the start node to each node. And keep in mind that this map will be a map of int to int, because we're always working with the IDs of the nodes in the graph, not the actual value. So I have it drawn as a map from string to int, but it's going to be from int to int, the ID of a node to the distance from the start node to that node. Because your values are going to be grid locations in the homework. I guess you could create a map from grid location to int, but I think you're going to run into some trouble if you do that. I would recommend just doing int to int. And we're ready to run breadth first search. So this is our setup. You're sitting down, you're ready to write task 3. You're going for it. You're ready. You're going to set up 3 data structures, a queue, a list, or if you want to get fancy and use a set, if you want to learn something, use a set, and a map. Initialize, mark the starting node as explored by adding it to your list. Set the distance of the starting node to 0, and in-queue the starting node. All 3 of your data structures are set up, they're initialized, you're ready to rock. And then you want to run your algorithm until the queue is empty. And since we don't, I mentioned it briefly earlier in the semester, but since we don't talk about while loops in 115, I'll briefly mention it, talk about it here. We want to run this while the queue is not empty. So a while loop, the syntax is just like that of an if statement. It's the keyword while, and then a Boolean expression, bless you, and that loop is going to continually loop until the Boolean expression is false. So as long as that Boolean expression is true, your loop is going to keep running. So we want to say well Q, and if you're using Scala's Q, you got the built-in not empty, well Q dot not empty, and then it's going to keep iterating until there's nothing left in the queue. And then inside that loop, you're going to do the logic that we're going to go through each node, whatever's at the front of the queue, we're going to process it, whatever's and all that processing is going to be the content of that loop. Hopefully I'm spelling this out enough how to write the code for breadth first search. There has been confusion in the past, so I walk you through it a bit these days. So we're ready. We're entering that loop. Well, the queue's not empty. Queue's not empty. So we're going to run a step of our algorithm. What we're going to do with that, when we're ready to run this thing, is dequeue the first element of the queue. So we're going to dequeue Carnegie, get it out of the queue, and process this node. When we process it, what we're going to do is go to our adjacency list to find all of its neighboring nodes, any node connected to this node by an edge, and then for each one of those nodes, we're going to check if that node is explored or not. These nodes are not explored, so if we find a neighbor that has not been explored, we're going to do three things, and those three things are exactly updating our three data structures. We're going to mark that node as explored, so we're going to add it to our explored list. We're going to enqueue that node in the queue, and we're going to update the distance of that node. The distance of each node that is explored is going to be the distance of the node that explored it plus 1. So if we have the distance to any node from the starting node, in this case 0, it is the starting node, but if we have the distance from the starting node to a particular node, and from that node we explored a new node, well, we can take the path that we found from the starting node to that node, and then we took one more edge to find a new node, so it must have the distance of the node that discovered it plus 1. In Q case, Harvard wasn't explored, mark it explored, enqueue it, update its distance to the distance of the node that explored it plus 1. DQ case is going to check all of its neighbors. Lincoln, it's going to do the same thing, mark it as explored, enqueue it, and update its distance to the distance of the node that explored it plus 1. So we know the distance from Carnegie to Lincoln is 2. This is something that breadth first search is going to guarantee us. We're going to find those minimal path lengths, which is we're using for distance right now. And case is also going to check Carnegie. It's also a neighbor of case. So when we go to its adjacency list and we say, give me all the neighbors for case, we're also going to get Carnegie in that list. But we're going to check our list of explored nodes. We're going to say, hey, list of explored nodes, do you contain Carnegie? And it's going to say, yeah, I already got a Carnegie in here. So we're going to say, cool, nothing else to do. If you're looking at a neighbor that's already been explored, do nothing. Nothing at all. If it hasn't been explored, mark it explored, enqueue, update distance. If it's already been explored, nothing. There's nothing to do. Don't have to do anything. We're going to dequeue Harvard and find BBN, ignore Carnegie, explore BBN, enqueue it, update its distance to Harvard's distance plus 1. And ignore Carnegie. And you'll notice as we go through the queue, just the way everything's set up, the way breadth first search runs, the fact that we use the queue to keep track of the order, what you'll notice is that we're going to explore all the nodes of distance 0. That's just the starting node, so that's not too interesting. Then we're going to explore all of the nodes of length 1. So our queue had case and Harvard. We checked all those. They were both the front of the queue. and then all of the nodes of length 2, or distance 2, then all the nodes of distance 3, then all the nodes of distance 4, then all the nodes of distance 5. We're going to explore them exactly in that order, and that's just part of the property of this algorithm. That's the order in which we're going to explore them if the queue is set up properly and we're following that ordering. So we're going to explore our first node of distance 2. We're going to explore MIT at this point. The queue that you have on screen is the right side where the nodes are in-queuing into the queue. Yeah, so they're in-queuing on this side and de-queuing from this side. So this side's the front of the queue, and this side's the back of the queue. So I'm going to de-queue Lincoln, and at this point we can see where we're going to discover MIT. We're going to explore MIT through Lincoln, because Lincoln is the front of the queue. So in the last run of breadth first search, I just said, well, the tie is going to be broken arbitrarily. We're just going to pick one of these things. We're just going to pick either Lincoln or BBN to explore MIT, and I just picked Lincoln. With the queue, in your code, you can't just code up, pick one arbitrarily. I mean, you can, but it's not what we're trying to do here. But the code is going to determine which node discovers MIT based on the order in which you added the edges into your graph. So it's still pretty arbitrary to us, but the order in which you added edges to your graph when you created the graph. So when we had Carnegie's adjacency list, if that list, the way I did the slides, that list was Case, then Harvard. So Case made it into the queue before Harvard, then Lincoln made it into the queue before BBN, and Lincoln is going to discover MIT. If that adjacency list were Harvard, then Case, it would be the other way, and we would discover this path to MIT through BBN. Either way, it's distance 3. We don't really care for our purposes, but that's how the tie was arbitrarily broken. It just matters how you added the edges. The order in which you added the edges to the graph is going to determine the order in the adjacency list, and that's going to end up breaking the ties in this kind of arbitrary fashion. But Lincoln made it first, so Lincoln to MIT. MIT marked as explored, in-queued, distance is Lincoln's +1. Case was ignored. DQ BBN, our last node of distance 2. We're going to find Rand, ignore MIT, ignore Harvard. Rand, distance 3. We have both of our distance 3 nodes in the queue right now. DQ MIT, ignore Lincoln, ignore BBN, discover Utah, mark it as explored, in queue, update its distance to MIT's distance +1. Explore Rand. Rand gets to explore 3 different nodes. Again, the order is just going to be determined by the adjacency list, and for our purposes, the order doesn't matter. Any order that we get these 3 nodes in is going to be fine, because we're going to mark all of them as distance 4. They're all going to be distance 4 in our distance map, no matter which one was processed first. They're all going to be Rand's distance, which is 3 + 1. DQ Utah, we're going to find our first distance 5 node, in-queue it, mark it as explored, update its distance. UCLA, our last, not our last. UCLA is going to discover Stanford, ignore SRI, ignore UCSB, ignore Rand. Mark Stanford as explored, in queue, get its distance of 5 out there. And now at this point, we can look, we see everything's explored, we have all our distance information. For all intents and purposes, we're done with the algorithm. But in your code's still going to run through these last nodes until the queue is empty. I mean, unless you could add some extra logic in there to say, oh, all the nodes are explored, we're done here, and then exit. But the straightforward way the simpler way to code it, I guess, your code's going to still look through this queue. If you're doing well, the queue's not empty. UCSB, we know none of these nodes are going to do anything, but they're still going to run. UCSB, dequeue it, explore all of its neighbors. UCLA, explored. SRI, explored. Rand, explored. They're all explored, so we're just going to skip them all and do nothing. SDC, Utah's explored. Rand's explored. Don't do anything. SRI, UCSB's explored. UCLA's explored. Stanford's explored. Utah's explored. Don't do anything. Stanford, UCLA's explored. SRI's explored. Don't do anything. Now the queue's empty. Your while loop's going to break. And now at that point, your breadth first search while loop is done. And you have a data structure, a map, which is going to tell you the distance from the start node to any other node in the graph. So for your homework, you start at the start node, the start grid location, run breadth first search, get this graph, get this map, which is going to tell you the distance from the start grid location to any grid location in the game, and then look up in that map, say, okay, give me the distance of the end location that I'm looking for, and then return it. That's your answer. Any questions at this point? That's task 3. Distances are cool, but what we really want is pathfinding, right? So how are we going to use this information? How are we going to use breadth first search to actually find paths? Like that was fine for distance. But for paths, let's change this map a little bit. And instead of keeping track of distance, which is the node that explored its distance. Man, I keep stepping on that. The node that explored its distance plus 1. Instead of doing that, let's just straight up remember the node that explored it. So for each node, we're going to remember how we got there. Which node was it that found this node? So for most of them, we don't know yet when we start the algorithm. But for the start node, we do know. And we're going to mark this specially as the start node. In my code, I like to use -1 for this. All the IDs for all the nodes in the graph in your homework, they're all going to be non-negative. So if I use -1, I know that's an ID that won't match any ID in my graph. And I can have a little logic that says, if -1, I know this is the start node. So some way, you can do it however you prefer. That's what I recommend. But somehow mark that as your start node. And then for each node you explore, keep track of the node that explored it. So when I visit Case in Harvard, instead of putting 1 here for distance, we're going to keep track of the node that explored it. Carnegie in this case, or in your code, the ID of the node that explored it. So whatever Carnegie's ID is, so you have whatever Harvard's ID is, mapping to whatever Carnegie's ID is. So you have a map of int to int. Again, we're always working with IDs in our graph, the ID of each node. And we run through breadth first search the same way. We would have our queue and our explored and our map. Same thing, except we're going to track the node that explored each node. So we run through this. Case discovered Lincoln. So Lincoln was discovered by Case. MIT was discovered by Lincoln. Rand was discovered by BBN. BBN discovered by Harvard, et cetera, et cetera. We'll run through the whole thing and get the same paths that we traversed, but we're going to keep track of different information in our map. Keep track of the node that explored each node. All right, that much sound good? And then we want to find the path between any, from the start node to any node that we choose. I'm going to choose Stanford. Oops. I'm going to choose Stanford. So now to take this information and actually compute the path, like we're only storing the previous node of each path. So how do we get this to actually be the paths that we're looking for? Well, we're going to start backwards. We're going to start at the end of the path, our target location. For our AI, this would be the closest player while avoiding walls. I want to know how to get to that player. What's the path to get to that player? Well, I'm going to start at that player. I'm going to start at the end. And that's the last link in my linked list, because the method should return a linked list, just like your compute path in task 1, except we're avoiding walls now, so there's a lot more complexity going on. We're going to start at the end and then prepend the previous node to build the path. So I'm starting at Stanford. I'm going to look up in my map, okay, Stanford. How did I get to Stanford? I got to Stanford from UCLA. So prepend UCLA. How did I get to UCLA? Well, I got to UCLA from Rand, prepend Rand. I got to Rand through BBN, prepend BBN. I got to BBN through Harvard, prepend Harvard. I got to Harvard from Carnegie. And Carnegie, how did I get to Carnegie? It was the start node. So this is where I'd have my if the previous node is -1, that's my start node, and that's where I end. Now I have the path. I have a shortest path from the start node to any node in my graph by taking a look at this map and then building my path backwards. Yes? Mm-hmm. Yeah. Yeah. So this would be the integer IDs for each node instead of the names themselves. But in your code, it would be the int IDs. So like when I built the graph, I think I said UCLA is 0, Stanford's 1, SRI was 2. Maybe that's probably how I did it. You would work with those numbers, 0 through 12, instead of the actual strings in your code. Because if you write it to work with ints, then it would work in this example, and it'll work when your nodes are grid locations as well, which are going to be in your homework. So you could try, it's up to you if you want to code this as grid locations, but I think you're going to run into some issues if you do that. And your code would only be useful for grid locations. And that's the application objective. But wait. Jesse, you gave out this example about the old days of the internet and routing packets through the internet, but you're asking us to do this. So how are we going to do this for the homework? How are we going to deal with this, with grid locations and AI players and all that crap? Let's talk about it. So we're going to visualize this, like when we're playing the game, we see the game board, but we want to convert this into a graph. So to convert this into a graph, and there's a method in the handout code that's going to do this. I'll jump to IntelliJ and make that more explicit in a second. But there's a method, level as graph, in the AI game state class. You call that level as graph. And what that's going to do is return a graph of grid locations where each node is a non-wall grid location in the game board. And any two nodes are connected by an edge if and only if that's a valid move for the AI to take or a human player to take. So this node to this node is a valid move. If you're on this node, you can either move right or down. So the only two edges, its two neighbors, are going to be right and down. There's an edge between this node, an edge between this node, and no edges between any other nodes from that node. No other node is a valid move. The wall nodes, the wall grid locations don't even have nodes because they're not going to have any connections. We're not even going to add them to our graph. So now when an AI player wants to move, say this player wants to move, it's going to get its grid location, which when you find its player location, which you're just going to call one of your task 1 methods, get the player location for that AI out of the AI game state. Player location has an asGridLocation method, which just takes the floor of its x and y and creates a new grid location object with that. So you get the grid location for that player's location. That's going to be this node right here. Run breadth first search on that node. Find the closest player, and then use what we just talked about to build this path from that player to the closest player. That's the application objective. For task 3, you're given 2 grid locations. If I give you this grid location and this grid location, you'll start at one of them, run breadth first search while keeping track of the distances, and then ask that distance map, hey, what was the distance to this location? And it should return 5, right? 1, 2, 3, 4. I can count. That should return 4. That's the distance between those 2 nodes. So you get this graph. You take your start grid location, your end grid location, run breadth first search, and then look up in your map what's the distance. Or if you just want to go for the whole shot, you can compute the paths right away. Just start with the application objective. Because once you have the application objective, you'll have some code that takes 2 grid locations and computes the path between them, and then return the length of that path for task 3. So if you're planning on doing the AO anyway, you can do the AO first, or at least part of the AO first, and then task 3 is just the length of the path, instead of writing breadth first search once that keeps track of distance and once that keeps track of paths. Just do the one for paths and return the length of the path. So that one's up to you. So when we're running this game, when we're playing this game, as human beings, we like to see this. That's what we see is the game board. We visualize all the grid locations and the walls and everything. The AI doesn't see any of that. The AI just sees a graph. It's just going to see the graph. You're going to use that graph, run breadth first search on the relevant grid locations, which are just nodes in our graph, and then use that with the pathfinding we just talked about to be able to actually compute the path that your AI should follow, while avoiding walls, of course. And we can see this is a disjoint graph. We have, if your AI is right here and your target is right here, which somehow a player got into this area where they shouldn't be able to be, you're never going to find that in breadth first search. So the way I initialized my distances, I said that would be distance infinity, and that's my way of saying we can't get there. It's not part of the connected component for that AI. So they're not going to say, oh yeah, I can get over there. That's just not going to show up on any of your searches. Because we do have 5 connected components to this graph. So these triangles should be ignored by your algorithm, as long as you code things up the way we just saw. I'm not going to have any test cases where there's only one target and it's not in the connected component. I'm not going to get tricky like that. But your breadth first search just won't happen to ever explore those nodes, because it can't get there. It's not part of the connected component. All right, so in the code, let's ground this a little bit. In the code, in AI game state, which is I want to be right now. I'm just a little lost. Or am I in the wrong spot? What am I doing? I want distance. Distance avoid walls. Do I not have that in here?
No.
It's I have you right in that method header? Okay. But distance avoid walls will be in here, and it will take an AI game state as one of its inputs. So in AI game state, you're going to call level as graph on that game state that you get. Well, first you're going to, well, no, you won't. So you're going to call level as graph. That's going to return a graph with set up exactly the way we saw in the slides. Any grid location that's not a wall is a node, and it'll have an edge connecting all of the valid moves that it can make. So it's a graph of grid location, and each grid location is going to have an ID based on this equation. So whenever I need a node's ID, I'm going to call this method and take its x location plus its y location times the level width. And that's going to be the ID for that node. So this will be consistent throughout your code. You can take advantage of that. When you have 2 grid locations for task 3, you can call this method to get the integer IDs for those grid locations. Use those IDs in your graph. So you'll have call level as graph. Let me back up a little bit. You'll have an AI game state in 2 grid locations. And you want to find the distance between the 2 grid locations. You call level as graph. That gets you a graph with nodes and edges. You're going to call grid location to ID on both the grid locations that you have. That's going to give you the 2 IDs for the relevant nodes for that input. Pick one of them as your starting node. Run breadth first search, keeping track of distance, and then look up in your distance map, okay, what's the distance to this other ID for the other grid location that I have? Then return that. That's your answer. Any questions about that on the setup? There's often some disconnect on this one. So if there is disconnect if you're not ready to sit down and code test 3 right now, what are your questions? And by the way, you can reverse this too if you want to write the inverse of this. And if you have an ID and you want to know the grid location for it, you can invert this. It's usually not helpful, but some students do. I forget why, but it's not required, but possible. Questions? Or are we not using diagonal movements? If you want to add diagonal movements, you can just add those edges in the graph. It's all the same logic. As for why not, when I do add them, the AI tends to, like if they're hugging a wall and they're trying to make a diagonal movement, they'll get stuck on that wall. That is the practical reason why I don't add them. Yeah. Right. Yeah, they're not allowed. Oh, somebody asked in chat, why aren't we allowing them? Just makes things a little more complicated. Not too much so. Like if you want to take this game, if this code is a start and add diagonal movements, by all means, go ahead. It's not too difficult, but you have to have some way to not let them get hung up on walls. That? Good. I want to see it. I used to have that as an application objective in a previous version of this assignment. You get an AO for adding diagonal movements. Not this semester, though. All right. Have a great day. I'll see you all Friday.